cell area. So you look at this red box, and let's say the one side, this vertical side, it has 2 CPP because it's this are 2 transistors here. This is contact to contact, contact to contact. There are 2 contact poly pitch, so it's 2 CPP. Okay, and then the horizontal side, you see this is 1 from contact, this 2, 3, 4, 5. It's like 5 metal 1 pitch. So 2 CPP, 5 metal 1 pitch. So the cell area is this 2 CPP times 5 metal 1 pitch, and roughly metal 1 pitch is the same as the CPP in this case, and it's about 4F for 1 CPP. This is what we also discussed in the earlier lectures. I think I had one slide showing the Intel's design 22 nanometer. The metal 1 pitch is like 90 nanometer, while using the F is 22. So roughly this is 4 times. So if you use this, then you say this 2 times 5 is 10 CPP square, and each CPP is 4F. So you get 160 F square. Of course, this is for this ratio, like 2:1:1. If you size up the transistor, then you will get maybe 200 or even 300 F square. That's typically true for your L1 cache. You need to size up. So any questions here?
What is the ratio of M1 to CPP?
Roughly the same here. It says the same. So here the M1 pitch is not minimal. So this is because here you from here to here, because this transistor W over L is 2, so you cannot put minimal metal 1 pitch here. So this is a typical layout. Of course, in the reality, there are many different kinds of designs for the layouts. And here I just show another design. Let's say above 90 nanometer. This is smaller than the 90 nanometer, which we will have this kind of layout. But above 90 nanometer, actually you can have more compact layout like this. So again, in question for you, if you have this kind of layout, how do you figure out which is which? So it has labels here. Yeah. So again, very easy, right? This box must be the N well. So this is PMOS, okay? And you have the gate here, so that means the transistor here. So those are PMOS transistors, right? Q3 and Q4 PMOS transistors. And here this is the same gate, right? That means here this transistor must be the pull down. This is the Q1 and Q2 here. And then here this in this design, the difference is that the gate direction is different here. This is the gate is horizontal. This gate actually is the word line. And then you have Q5 and Q6 like horizontally. You have Q5 and Q6 horizontally. Oh, sorry. So the Q5 and Q6 actually is vertical. So because the gate is horizontal, so the Q5 and Q6 is vertical. So those are the pass gates. Oops. So those are the pass gates. Q5 and Q6 at the bottom. So this is more compact actually, this design. But this design is only adopted until 90 nanometer. Below 90 nanometer, and the industry give up this kind of a more compact rule because here you have less spacing. And here you look at this, there are many white space here. So there are some reasons. So, questions?
What's the darker diffusion layer means?
Darker diffusion. Diffusion means you have to dope source and drain. Diffusion region means source and drain active region and the channel, right? You need to dope source and drain.
I think they probably use diffusion like that. If it's a polysilicon, it's a self-aligned gate. This one. Because they say polysilicon and diffusion, so it's not specified whether it's N or P. This one.
Yeah, it doesn't specify N or P, but I think those are for the source and drain.
Yeah, it's self-aligned.
Yeah.
And why is the gate for the PMOS is not on top of the polysilicon, but right beneath? Yeah.
You mean why is this?
Yeah. Why the gate is not on top of the polysilicon?
Why this
the
is
diffusion?
the gate is on top of the diffusion, right? This is self-aligned process as he mentioned. So if you fabricate, I think I don't know if in the fabrication guest lecture talk about this or not. You fabricate the gate first, and then you use the gate as a mask to do the source and drain doping. Then you can protect the channel region, right?
So the underneath the poly is also diffused?
No. Under the poly, no. Under the poly, the channel region is your substrate. N-well, for example, the PMOS is N-well. And you only dope source and drain region by self-aligned process. You use the gate, polygate as a mask to dope source and drain. So the underneath the polygate is protected, you don't have dopant. But of course, later you do the annealing and then the dopant will naturally diffuse. So that's why you have the overlap between your gate and the source and the drain.
Why this not a P-well region for the NMOS?
Because the substrate is all P-type.
Oh, okay.
Yeah. You start with the P-type substrate.
So except the big box of N-well is all
Everywhere is P.
P-well. Except
P substrate, P-type substrate. The whole substrate is P. So you make NMOS. But if you want to make PMOS, then you have to create this N-well.
some N,
Usually, but most of the times. Most of the time, it's always P-type. I think very rare that they start with an N.
Yeah. Yes. Okay. So that's why I mean this cell layout relates to the fabrication steps, and also comes to the circuit. So this is a bridge between the circuit designer and the device fabrication engineers. So the layout is a bridge.
On the previous slide, why is the CPG 4F instead of, because half pitch is F, right?
No, this is in the logic design rule. It's not the DRAM. So here.
Oh, that's on the DRAM.
Yeah. So as we discussed, in that lecture before. So the contact gate pitch is roughly 4F. Yeah. Metal 1 pitch can be 2F in principle, but in this design, no, because here you cannot have 2F because W over L is already 2. Okay, so we will discuss why industry give up this kind of layout and switch to this one. So the key difference is that here you can see the direction of the transistor is different in this so-called tall cell is tall. Okay, so because those transistors, let's say gate are vertical, and then those two pass gates, the gates are horizontal. Okay, so this is not preferred when we move to the advanced technology node due to the difficulties in the lithography. So, but before we look at that, discuss that, I just want to show another example. So every foundry will have their own SRAM cell design rule. Those rules are actually different from your logical design rule because you have to make this more compact. So these are custom design rules. And this is just one example from the, I think, IBM's 45 nanometer design rule. So it will specify the distance between those different regions. I will skip the details. And if you open the library from each foundry's PDK, then for the SRAM design, it has specified design rules. So the challenge for the SRAM layout comes from the fabrication, the patterning. Patterning means the lithography. You define those patterns, define those shapes, like the gate or the shape of the gate. So this is I think this is the 65 nanometer from Intel. This is the image under the microscope from the top view to look at the cell layout. So I hope you can still correlate this image to the previous layout and the circuit schematic. So it's the same as before. So this is the gate, and this is a PMOS. This pull up, and this is a pull down, and this is a pass gate. If you still remember that this is pull down, this is a pass gate. Okay. So those transistors, you see, the challenge is that when you do the real fabrication, the shape of your gate becomes rough, and then maybe round shape at the end of the region. So this is due to the resolution problem in the lithography. And I hope you still remember the lithography. I mean the last lecture, guest lecture talked about this. So basically you shine the light through the mask, and then you have the lens, and then you can expose some of the features, patterns on the wafer, the photoresist. So since this goes through a mask, then due to the refraction of the light, then you have some certain resolution of the features. And this is, if you recall your college physics, optics, so this is a resolution of the, let's say you have two holes and the light goes through that. And this is, lambda is wavelength of the light. And NA, I think, is a numerical aperture for the lens. So the challenge is that the lithography we used today mostly uses 193 nanometer wavelengths. So, and this is roughly, let's say, half lambda. The resolution, if you use the optics, the standard college physics optics, so the minimal feature you can pass using a certain wavelength, lambda is half lambda. That is a resolution you can have. So that means 193 nanometer wavelength. Actually, you can only do like 90 nanometer technology node, roughly. So then, if you go beyond that, then due to the refraction, your pattern will be something like that. Will look ugly here. So this is a challenge. If you move further down, then in the technology node, then you basically cannot pattern this kind of features on your wafer. But the industry came up with many techniques to extend the lifetime of this 193 nanometer lithography. Even today's, let's say, 14 nanometer technology node, we still use this 193 nanometer lithography, the same wavelengths. So there are several key innovations. The first one is so-called the immersion lithography. So this is to, instead of, because here this one relates to the K value or the epsilon, the dielectric constant. between the, let's say, the medium between the lens and your wafer. And then if you use air, this K is roughly 1. And also, I think it's not K, I think it's in the NA. So there is a coefficient in the NA related to the dielectric constant of the medium between the lens and the wafer. And if you use air, it's 1. But if you want to improve that, you can use liquid between those. So then some kind of oil, I think, the industry uses some kind of oil. And this is called immersion lithography. So this can improve the resolution by 50% roughly, if you use the K value from 1 to 1.5. So this is one technique. The second technique is called the OPC, optical approximity correction. So this is a CAD technique to predefine the mask shape, considering this kind of refraction of the lights. So when you send the GDS file, as a circuit designer, your final product is a GDS file, and then send that file to the foundry. Foundry will make that mask for the lithography, but that's one additional step you can do there. So your mask may not be the same as your GDS file. You can do some correction there. For example, if you know at the end of the line there will be a round shape due to the refraction, you can purely calculate this by the optics using the physics, fundamental physics. So if you know this is the problem, then when you design the actual mask, you will design something like this at the end of the line. So even it will expand a little bit after the real fabrication, then you can still roughly get like a rectangle shape. So this is the mask. You will use this OPC to predict the shape, so you can do some this kind of correction before you do the fabrication. So this is the second technique. And third one is the double patterning or triple patterning. I will discuss that in a minute. And today, I think industry is switching from the 130 nanometer lithography to the 13 nanometer EUV, called the extreme UV. And so this is a big step. So I think Samsung, last month announced for their, and the TSMC as well, for their 7 nanometer, 5 nanometer process, they're going to adopt the EUV for the maybe 5 nanometer process and beyond. So, but before the 5 nanometer EUV is before this is mature, so what industry uses is this double patterning technique. So because we know it's very hard to pattern this kind of, if this is a final pattern, this is for the, if this is the final pattern we want, and we know the challenge is here. So what we want to do is to just pattern the simple features instead of this kind of complicated features. This final pattern is very complicated. You have different kind of shapes here. So it's, the easiest to do is just the straight lines. Okay. So then what we can do is to, let's say, split this into two steps. Right. First, you can pattern the horizontal lines like this, no problem, and then you etch those away by using another vertical lithography, the second step. And then you can etch, and you can do two steps, and then you can make this final pattern. So each step is simpler. Okay, you just do the straight lines. So this is a double patterning, and also for the self-aligned double patterning. So this is another technique to increase the density of the pitch. So if your lithography can only do this kind of pitch due to the resolution, and you can actually make smaller features using the double patterning. So firstly, you have some, let's say, sacrificial layer like this, some, let's say for example dielectric, and then you can pattern using your conventional lithography. And after that, you deposit some material, conformally cover this surface, and then we do edge, homogeneously edge. So you are going to etch away the top surface, but here, since you have higher thickness as a sidewall, so you still have something left as a sidewall. And then we remove this sacrificial layer by some etching. So what is left is this. And this can be your hard mask to further etch the materials underneath. So then you can get eventual feature like this. You look at the density of the pitch. Previously is from here to here, now it's from here to here. So basically this is the way you use the sidewall to transfer the feature, and then you increase the density of the pitch.
Is this SAQP, I think it's called?
Yeah, this is in the second slide here. So this is called the, if you do single lithography, this is as conventional, and if you can do this self-aligned double patterning for the SADP, then you can increase the density, and then you can do 3 times, triple or quadruple. You can do 3 times or 4 times. So then you can get a very small feature. That's how the industry make today's like 14 nanometer transistor using 193 nanometer lithography. So this is combined with the OPC and the double patterning, triple patterning. So this is a technique. And but I think this is the roadmap for the lithography. And today, I think the industry is switching to this EUV. This EUV is extremely expensive. Only, I think, TSMC, Samsung, Intel can afford those tools. So this is the state of the art. Okay, I think we can stop here today.